All right, Unit 2, Section 3, Graphing Polynomial Functions. All right, so as a quick warm-up, give the real zero of each function. So here we are again, zeros, x-intercepts, solutions, roots. But where do they come from? They come from setting the function equal to 0 and solving for x. We like when functions are in factored form. Then it's just the opposite of what the factor is. So x is equal to 7, and this is a double root because this exponent, my exponent of 2, and then I get x is equal to negative 1/2. So those are my two zeros. For part B, set that equal to 0. Now I do need to factor. Okay, so there's a GCF of x, so I'm going to take that out, leaving me with x squared plus 2x plus 1. Factors of 1 that add to 2 are 1 and 1, so this is a perfect square trinomial, so I can go right to that. So I have x is equal to 0 and x is equal to negative 1, and again that's a double root. Okay, lastly, we've looked at these a little bit. When I have a polynomial with 4 terms, let's first start factor by grouping. Okay, this will not always work, but it's going to work today. The first 2 terms have an x squared in common, leaving me with x minus 5. Now the whole point is to get what's inside those parentheses to be the same. So I exactly have x minus 5. So for my factored form, that would represent a plus 1. Okay, so I have x minus 5 times x squared plus 1. Set that equal to 0. So I get x is equal to 5 as my real 0. Because if I attempt to solve that for x squared equals negative 1, this would give me a non-real solution. So I don't get any real zeros from that factor. Okay, we got a lot going on here. A couple things I need to point out, and we'll talk about this more in class. End behavior. What happens at the ends of the graph? It all depends on the degree and the lead coefficient. Our degrees are either going to be odd numbers or even numbers. Okay, what's the degree? Highest exponent of a polynomial. Our lead coefficients are either going to be positive or negative. Okay, those two things will always be true about a polynomial function. Degree is going to be even or odd. Lead coefficient is going to be positive or negative. So the short of it is, depending on the degree and the lead coefficient, it tells us what our end behavior of the graph is. So end behavior meaning the ends of the graph. So we call that, if it faces down, we would call the end behavior down up, because we always increase x. Okay, so as x increases from a negative to a positive. Odd degree, negative lead coefficient, my end behavior is up, down. Even degree, positive lead coefficient, my end behavior is up, up. Even degree, negative lead coefficient, my end behavior is down, down. Now the next slide gets into a whole lot more detail with this, but check out what's happening. Okay, it's dotted in here because that's not to say that every single function is going to look like that. The only thing that has to be true is that the end behavior has to be set. Okay, now the next piece of information, which again, when we look at the graphs, it'll make more sense. An even power function, and I'm even going to say an even power factor for this. The graph is going to bounce off the x-axis at that root, at that 0, at that x-intercept. If we have an odd power factor, when we go to graph the polynomial, the graph will go through. It'll cross through the x-axis. And again, these will make more sense when we look at our examples. Okay, so the long of it, all right? This nice chart gives you functions from linear to quartic, and it gives you examples of what all the different functions can look like. Okay, so here's our degree. That never changes. We have turning points, we have end behavior, and we have the degree. And this is all listed. And you're going to see that when we start graphing these functions, they're going to correspond to exactly what one of these possible graphs looks like. Okay, so these are right from the textbook. Okay, we're going to do 4 problems together. So first we find the zeros, x-intercepts, roots, solutions, all right, whatever you like to call them. It's in factored form. We love that. So -1, +2, +4. All of these factors have odd exponents to them, meaning all of these are going to be cross points, meaning they're going to go through the x-axis. Next, we're going to incorporate this more. The domain of this polynomial, every polynomial has a domain of all real numbers. Okay? What does that mean for the graph? It means the graph is going to be smooth and continuous. The domain will really come into play when we look at rational functions, so functions that have a numerator and a denominator. But we want you to be exposed to understanding and finding the domain of all types of functions. Okay, so the fact that the domain is all real numbers, when we go to graph this, I never have to lift my pencil off the paper. All right, next thing, the degree. Oops, went right ahead. The degree of the polynomial is 3. The degree simply comes from adding up the degree, the exponent of each individual factor. So the degree is 3. My lead coefficient, we know if a number is not written, it's known to be 1. So my lead coefficient is positive. Okay. So I guess if I'm going in order, zeros, identify the domain, identify the degree and the behavior of the lead coefficient, and now we go to graph. So the easy part is actually putting on the x-intercepts. -1, +2, +4. All of these are going to cross through the x-axis. We're not going to have any bounce points. Now let's check out the m behavior. So I have an odd degree, positive lead coefficient. So my m behavior is going to be down, up on the graph. Okay, if it's down, up, I start there. I'm drawing a smooth and continuous curve, and I have to make sure that I cross through each of those x-intercepts. And that's it. Okay, you are not responsible for understanding what these y values are just yet. So sure, you can draw it. It can be much bigger. Okay, maybe it can be even closer. What stays the same is that if these are x-intercepts, that eventually I'm going to have a turning point to get back to these numbers. Where those turning points occur, you don't know yet, and you're not responsible for knowing right now. We're just sketching based on the general behavior of what all polynomials have. Okay, so first zeros. X equals 0, x equals -5, x equals -3. Each of these individual factors are to the first power. Domain, like all polynomials, all real numbers. I'm just going to continue to write it though. Our degree is 3. But now our lead coefficient, the lead coefficient is a -1. So now A is less than 0. Okay, so going back, odd degree, lead coefficient negative. Now my m behavior is going to be up, down. Okay. 1, 2, 3, 4, 5. -5, -3, 0. If m behavior is up, down, I have to start above the x-axis. My smooth and continuous curve. Verifying in here. Up, down. The m behavior matches. Each of my individual factors had an odd exponent, so they're all cross points, not bounce points. So you're going to see that these graphs really all start to look the same. Okay, example number 9. Zeros, x equals -1, x equals 2. Domain of the function, all real numbers. Now my degree is 4, because 3 plus 1 gives me 4. And my lead coefficient is positive, right? Because nothing's written out front, so we know it to be positive 1. So even though the individual factors are going to be cross points, now my degree has become an even number. Let's go back. Degree is even with a positive lead coefficient. My end behavior is going to be up, up. Okay. -1, +2. End behavior of up, up, crossing through both of these x-intercepts. It's going to look parabolic. It's going to resemble a parabola. Okay, up, up, 2 x-intercepts. Done. Last example. Now this one asks us to, or you first, in order to find the zeros, you first have to factor it. So x squared in common, leaving me with x squared minus 1 when I factor that out. X squared minus 1 is the difference of perfect squares, so that factors to x minus 1, x plus 1. So my zeros are 0, 1, and -1. Now this is different here. This is where I have an even exponent on the factor, so I'm going to have a bounce point at 0. All right, I'm going to write that down. This is going to bounce at 0. These two are going to cross over the x-axis. Okay, domain, all real numbers. My degree. The polynomial is in standard form, so I can take the degree right from the original, which is 4. Or if I add these together, 2 plus 1 plus 1 verifies the degree is 4. Lead coefficient is positive. So it's going to have that same end behavior as the previous one. The end behavior has to be up, up, because it's an even degree and a positive lead coefficient. Okay. -1, 0, +1. Now look what happens. So I start up. I cross at -1. Oops. Let's make that a little nicer. I cross at -1. I bounce off the x-axis at 0, and then I cross again at +1. Okay, so cross, bounce, cross again. It verifies everything I need. My end behavior is up, up. Because this degree is 2, it's an even number. This is a bounce point. So all those things for you to be aware of. Okay. All right, so please try for homework. I think it's page 66, whatever section 2-3 is. Numbers 2 through 12 even. So they're all in factored form. So you're going to identify the zeros. I want the degree, the lead coefficient, and then you're going to sketch it. The domain of all of them are all real numbers because they're all polynomial functions. Okay, see you in class.